All right, today's lesson is titled Experimental Probability and Relative Frequency. Just the other day, we worked on theoretical probabilities. So as we work through this lesson, I want you to think about how theoretical and experimental probabilities are similar and how they're different. And how does relative frequency fit into all this? You'll see that we have 3 goals today to work on. At this time, please make sure that you have your Unit 8 probability notes out next to you. They look like this. We already started working on them. We're going to finish them up today. And we're going to start our lesson with these 4 games of chance. So they're on the back side of your notes. Normally, if we were in the classroom together, you would run these 4 games of chance with your elbow partner and record your data. Unfortunately, we can't do that right now. So we're going to run these 4 games of chance using my data. And my son Trey is going to help us out. So for each game of chance, please make sure you record in just like Trey does to represent the data. Game of chance number 1, flip a coin. Heads. Yep. Heads. I'm making sure it's flipping heads. Ooh, that was a good one. Tails. Tails. Heads. Tails. Heads. Tails. Heads. Awesome. We're going to go to rolling a die. Here we go. Roll 1, 6. Ooh, whoopsie. Sorry, computer. Roll 2, 1. 1? Yep. Roll 3, 1. Roll 4, 6. 3. 5. 6. 6. 2. 1. Pick a card color. So we have 52 cards in a standard deck with jokers removed. We are going to see what are the chances we get a red or a black colored card. So I'm going to do a quick shuffle of my cards, making sure that the jokers have been removed. Okay, and then every time I pick a card, I have to replace. Otherwise, there wouldn't be 52 cards in here. So here we go. First draw, which is a red. So R for red. Replace the card. Next draw, black. Replace the card. Next draw, black. Replace the card. Next draw, black. Replace the card. Next draw, red. Replace the card. Next draw, black. Replace the card. Next draw, black. Replace the card. Red. Called Jack. Replace the card. Red. And last draw for our 10 draws is black. All right, now we're picking a card suit. So we have clubs, spades, diamonds, hearts. Here we go. Again, 52 cards in a deck with the jokers removed. I have to replace the card. Otherwise, I'm changing my sample space. So here we go. First draw, we have a heart. So put a heart. H for heart. Replacing the card. Second draw, we have diamonds. D for diamonds. Third draw, after I replace that card, we have hearts again. Third draw, we have, that is what we call a spade. So S for spade. Replace the card, we have hearts. And the 5th draw. 6th draw, we have hearts again. Next draw, we have diamonds. Next draw, we have, that would be clubs. So C for club. Next draw, that is a spade, S. And our last draw for this game of chance, D for diamonds. Thank you, helper Trey. All right, so we are going to fill in our vocab at this time, so please find that chunk in your notes. Experimental probability is the chance of something, an event, happening. You might go, Ms. Luer, how's that different from theoretical probability? And well, experimental is what actually happens. You need to fill in the word actually. Theoretical is what the math says should happen. Experimental is what actually happens. Relative frequency is a synonym for experimental probability. It is how often something happens divided by the outcomes. So another name for relative frequency would be experimental probability. They're one and the same. Flip to the back of your notes and find this ratio in the chunk for experimental and relative frequency. So we have, for experimental and relative frequency, we're looking at the number of times an event occurs divided by the total number of trials. Again, we can say, write this in, we can say it's what we want over the total. It's still what we're looking for, what we're focused on over the total number of outcomes. Now let's go back to our games of chance. You'll see In that chunk in the back on your notes, you have this chart, and it has the columns titled Game of Chance, Event, Relative Frequency, Experiments Probability, and Theoretical Probability. I want to start by filling in the theoretical probability side. Flipping a coin. What is the theoretical probability that when you flip a coin, you get heads? The event is heads. Well, how many heads are there? 1 out of how many total outcomes are there on a coin? 2. Get heads or tails. Let's change this to a percent. So on your calculator right now, go numerator divided by denominator, and then move it, move it. 1/2 is the same as 50%. Okay, let's go to roll a die. We want to find the theoretical probability you roll a 6. What I want over the total. So what do I want? I want a 6. How many 6s are on a die? A fair die. 1 out of what are the total number of outcomes on a die? You could roll a 1, a 2, a 3, a 4, a 5, or a 6. So that's 6 outcomes. 1 out of 6. Let's change this to a percentage. So numerator divided by denominator. Move it, move it. Once you get it to the decimal, you got to move it, move it. So 1 divided by 6, you get 0.16666, and then your calculator rounds up, right? Yep. So if we move it, here let's make sure we round to the nearest percent. So if I have, up here I'll do it, 16.6 repeating percent, and I want to round to the nearest percent, I'm going to underline the digit. Rounding to the nearest percent is like rounding to the ones place, and look next door, is it 5 or higher? Then I'm going to add 1 more. So it's about 17% of a chance of rolling a 6 on a die. If you think about your probability number line from the theoretical probability lesson, this would be an unlikely chance that you would roll a 6. Next, let's go to pick a card color. The event is, what are the chances that you pick a red card in a standard deck of cards? Well, first of all, how many reds are in a deck of cards? There are 2 different colors that make up a deck of cards. You could have red or you could have black. So half of the deck of cards is going to be red. How many total cards are there in a deck of cards? 52, because we take out the jokers. So what's half of 52? 26. 52 divided by 2 could give me 26. So I need to simplify this ratio. 26 to 52, Miss Kluver already said it, that's the same as a half. And then I need to change that to a percent. So 1 divided by 2, that's your decimal, move it, it's equal to 50%. Pick a card suit is the next event. I want to know what's the probability you pick a diamonds. Now there are 4 different card suits in a deck of cards. So you want to think about the deck is cut into fourths. There are still 52 cards in a deck, but I only want a quarter of them. How many cards in a deck are diamonds? Well, if you take 52 and divide it by 4, you'll learn that there are 13 cards in a deck that make up each suit, since there are 4 suits in a deck. Now we can simplify this. It doesn't look like you can, but you can. If you take 13 and divide it by 13, you're going to get 1. If you take 52 and divide it by 13, you're going to get 4. Okay? And then 1/4 as a percent. Well, first let's take it to a decimal. 1 divided by 4. What is that? 0.25. Move it. So 25%. The only one I had to do an round to the nearest percentage on was rolling a 6 on a die. These are the theoretical probabilities. Let's circle the percentages. The theoretical probabilities for these events. But now, what is the relative frequency or experimental probability for these same events? That's when we're going to have to use this data, okay? Right now, look, how many times did I flip a coin? 10. How many times did I roll a die? 10. How many times did I pick a card color? 10. How many times did I pick a card suit? 10. So our denominator for each one of these events is going to be 10. Right now we're using this ratio for experimental probability, the number of times an event occurred, what I want, over the total number of trials. Well, I only did these games, each game 10 times. So that is my denominator. Now, if we look at our data, the experiment's probability that I flipped and got a heads, well, how many heads did we get? 1, 2, 3, 4, 5, 6. So the experimental probability that I get heads is 6 out of 10. Let's change this to a percentage. 6 out of 10, 6 divided by 10 is 6/10. Move it. 60%. Let's go to the next game of chance. What's the experiment's probability? I roll a 6. Here's the event. It's already given for me. So if I go and I look, what's the experiment's probability that I rolled a 6? Count the 6s. 1, 2, 3, 4. 4 6s. That's what I want over the total number of trials was 10. So 4 out of 10, change that to a percentage, 4 divided by 10, or if you're using the proportions, what times 10 is 100? 10, so you can take 4 times 10. That would be 40%. Let's go to the second to last game of chance, which was pick a card color. I want to know what's the probability, the experiment's probability that I picked a red. So we have to actually look at what happened and use that information. Red would be 1, 2, 3, 4. 4 of my trials came out with red. So if I change this to a percentage, 4 out of 10, what would that be? My experiment's probability is I'm picking red 40% of the time. Let's do our last game of chance, which was pick a card suit. We're looking for the probability of picking a diamonds, and this is going to be the experiment's probability or relative frequency. Again, relative frequency and experiment's probability are one and the same. How frequently did I get a diamond? So we have to count those. 1, 2, 3. So the frequency for getting a diamond is 3. The relative frequency for getting diamonds would be 3 out of how many total times did I play this, or how many trials do I have here? 10. Also, I could say the experimental probability of getting a diamond is the same, 3 out of 10. But 3 is the frequency, and that's why relative frequency and experimental probability go so nicely together. You can call them synonyms of one another. So changing this to a percentage, 3 divided by 10 is 30%. So right here, these percentages are experimental probabilities, and over here we have the theoretical probabilities. Are they the same? Why or why not? Think about that for a moment. So are those probabilities the same? I asked you to think about it for a moment. Before we talk about that, I'm going to have you edit something in on your notes. Mrs. Kluger forgot to have you simplify our relative frequency experiments probability ratios for 3 of the games of chance. The first one, 6 to 10, we can simplify that to be 3 to 5. So will you make that edit in your notes as well? For rolling a die, we can simplify our relative frequency of 4 to 10 to be 2 to 5. And for pick a card color, we can simplify that to be 2 to 5 as well. So put in those edits. Ms. Kluber, why do I have to simplify the ratios? Sometimes it's easier for our mind to focus on the simplified version of the ratio and comprehend it. Just like I shared with you how it's easier for my mind to focus on probabilities when I'm looking at a ratio or a percentage. How we look at numbers, it can help how we understand the numbers. So that's one of the reasons why we simplify. Now, are these probabilities alike? Meaning, relative frequency, experimental probability, are they similar to theoretical probability? Yeah. All these probabilities talk about the chance of something happening. Are they different from each other at the same time? Yes. Theoretical probability is what the math says should happen. Experimental probability and relative frequency is what actually happens. Yes, the math says I should get heads 50% of the time, but look at what we got it. We got it 60% of the time because it's what actually happened. So these probabilities are similar and they're different. So is 10 trials of something, like I did the 10 trials of each game of chance, is that enough to make a good prediction for probability? And this question would be much more beneficial if we were all working together right now. And it kind of fits hand in hand with these two types of probabilities. So I'm just going to jump into it. Would it be fair for me to give you a report card, so your grade for the quarter based on one test or one assignment? You'd probably say, no, Mrs. Cliver, that would not. And I wouldn't want that, Mrs. Cliver. I'd agree with you. Would it be accurate to say that a coin will always come up heads after flipping it once? No, and we have room to prove that, right? We did 10 trials of it. How about this one? If 50% of the students in a class said they like country music, does that mean 50% of the school likes country music? Not necessarily. We need more data to support. And that's what these questions are alluding to, sixth graders. So if we were doing this activity in class, which I normally do, I would then take the 10 trials from each person, we would put those together, we would calculate the experiment's probability, and what we would see would lean towards the experimental probability for these games of chance in front of you, their probability being even closer to the theoretical probability. Because numbers can't lie. People can manipulate numbers, but numbers can't lie. So what the math says should happen is what will actually happen the more trials you run. So what I'm trying to say, the more experiments you do with experiment's probability, the closer and closer you're going to get to the theoretical probability. Because again, numbers, well, they're not going to lie. So there is one more part in your notes. It says theoretical versus experimental. How would you explain the two types of probabilities to someone who has never heard of them before? Write 1 to 2 sentences down there about how you would explain these two types of probabilities to people.